Good evening. We are continuing with synchronous motor drive. In the last class, I had told that we would be working out one numerical example on variable frequency control of synchronous motor drive. We had already looked at V by F control. So in V by F control using a VSI, what we said was until the rated speed, we are going to have voltage and frequency increased in proportion to each other. They are going to be increased in proportion to each other. So this will ensure that V by F ratio, if it is a constant, then we are going to have the flux to be a constant because flux is going to be voltage divided by frequency approximately. So due to which this will be held as a constant. Whereas if we are looking at operation above rated speed. So whenever we want to have operation above rated speed, then we necessarily need to increase the frequency. The frequency will be increased, but voltage will be frozen at rated value. So we are going to have V by F ratio. If I try to look at it, V by F, F is increased, whereas V is a constant. So due to which flux will decrease. So this is what we call as field weakening region. So under this condition, very clearly, because the flux is decreased, the torque capability will also decrease. So this is very, very similar to the operation of an induction motor drive. It's not very different from that. But only thing is, because the speed of a synchronous motor drive is directly dependent upon frequency, we will have very, very accurate speed control. But whenever we are going to vary the frequency, there will be hunting oscillations at every step before it settles down to a new speed which is corresponding to the new frequency, right? So this is the way it is going to function. If we actually look at the original equivalent circuit, what we had drawn for the synchronous motor drive, we said that we are going to have a field current, which is actually supplied in the form of DC current. Its equivalent AC current has to be taken, which is IF dash. And we generally know that if we are going to have the flux along this direction, the field current is along this direction, then we are going to have EF, that is the excitation voltage is going to be along this direction, right? If this is direct axis, this is going to be along the quadrature axis. Okay. And if we say normally that the excitation voltage is at an angle which is corresponding to minus delta, which is the load angle. So that is actually E angle minus delta. So very clearly IF will be minus delta, and this is another 90 degrees away. So we have to write this as IF angle minus delta minus 90 degrees. That is how it will be. And if this is the field current that is being pumped in, this is going to actually cause a flux which is actually mutually linking between the rotor and the stator side. So if I say that the stator is being applied with the voltage which is corresponding to Vs, that is the reference. So this is Vs angle 0. That will actually have some amount of resistance drop. If we consider resistance to be negligible, we'll have at least a leakage reactance drop, and that is essentially going to pass a current in this direction, which is IA, which is the armature current. So this is going to be XL, that is the leakage reactance. So this is what we drew as the equivalent circuit, if you may recall. And we said that if IA is flowing in this direction and if IF dash is flowing in this direction, both of them together, this is going to pass through this, which is actually IM, which is the total current, which is IA and IF put together. Now, if we consider this portion, this complete portion as a Norton's equivalent circuit, which is consisting of a current source and an impedance, this can be replaced by a Thevenin's equivalent circuit. So I should be able to draw it somewhat like this. This is XL, and I'm going to have XM here. And here Xm multiplied by IF, that is what is E. So I can write here this as E angle minus delta. And this side what we have is going to be Vs angle 0. And this will essentially be connected together. Now these two put together, we can call that as the synchronous reactance, XS. Okay. So if I translate this into phasor diagram, if let us say I'm going to have the armature current somewhere here, let us say this is the armature current. So let me call this as IA. Now, when I look at the summation of IF dash and IA together, that is what is IM. We already said that this is IM. So let me just draw the summation of these two. So this is going to be IM. This is going to be IM. Okay. Now, if I have IA to obtain what is Vs, I should say E angle minus delta plus JXS times IA is going to give me IA angle phi, in fact. This is IA angle phi. That is going to give Vs. So let me draw that clearly here. This is IA. So if I want to get what is IA multiplied by XS, that should be 90 degrees leading. So I should actually draw this here. Exactly the same thing I should draw here. This is JXSIA. Okay. So when I add these two together, I am going to have this as Vs. This is going to be Vs. Okay. And between Vs and E, the angle will be delta. That is the load angle delta. The same way, IF and E are perpendicular to each other. Vs and Im are perpendicular to each other. So between these two, we are going to have the angle delta again between IF dash and Im. And between V and IA, the angle is phi. That is what is the power factor angle phi. It is a very small angle that is visible in this diagram. That is the power factor angle phi. But between IF and IF dash and IA, we call this angle as delta dash. So I should be able to write E is equal to J times XM. Rather than writing XM, because XL is very small, I'm writing XS multiplied by IF dash. Whereas if I try to write what is Bs, that will be J times XS times IM. where Im is the summation of If and armature current, Ia. Now, if we are doing variable frequency control, Vs will change in proportion to frequency. Similarly, Xs will also change in proportion to frequency. So also is the case with respect to E and Xs here. So if I say that I'm going to have the frequency currently what is being applied to the synchronous machine divided by F rated, if that is equal to A, I can write these two equations somewhat like this. I can write A times E. That is, whenever I'm talking about another frequency F, the value of E will also change to A times E. That will be equal to J times Xs multiplied by A multiplied by If dash. Similarly, A times Vs will be equal to J times Xs multiplied by A multiplied by Im. So whenever the frequency changes, actually it is not going to impact the currents. It will only impact the voltages. So if the voltages are increased, we are going to have this extending further and further. This will also extend further and further. JISXA will also extend further and further. So we are not going to have any variation in the currents, neither are we going to have any variation in delta. So in V by F control operation, there is no change in the flux, in the currents, and torque. And we should also say no changes in angles. Any of the angles, they are also not going to change. But the voltage magnitudes will change. That's what happens in variable frequency operation. Okay. So let us have this concept in mind and try to look at one numerical example in the variable frequency control of synchronous motor drive. So let me first of all give the problem statement clearly. So the problem statement is somewhat like this. It is the same motor we had considered in an earlier problem. So this is a three-phase 6.6 kilovolts, 1.1 megawatt, 60 hertz, 6-pole, UPF, Y connected, synchronous motor drive. This has an excess value of 36 ohm, nominal field current is 12 ampere. It is 12 ampere. It is controlled by V by F control using a VSI until rated speed. Above rated speed, V is frozen at rated value of 6.6 kilovolts. Now, what is being asked is calculate first subdivision is IA, delta, and power factor at full load torque and rated excitation when the speed is 600 RPM. So this is the first subdivision. So let us try to solve this first. So the first thing what we want to calculate is what is the rated armature current. That is going to be the power divided by root 3 VL cos phi. So we are essentially using the expression power equal to root 3 VL IL cos phi. So we are actually looking at IL. So IL is going to be power divided by root 3 VL cos phi. Power is 1.1 multiplied by 10 power 6 divided by root 3, 6,600 volts, which is the line voltage, and cos phi is unity. So this comes out to be 96.225 ampere. This comes out to be 96.225 ampere. Okay. Let us also calculate what is the torque. So rated torque will be 1.1 multiplied by 10 power 6 divided by whatever is omega s. And omega s in this particular case is 1200 RPM because it is 60 hertz and 6 pole, which happens to be 125.66 radians per second. So we can use that 125.66 radians per second here. And that will give us the torque value. And the torque value happens to be 8753.8 Newton meter. That is the rated torque value. Now, let us first of all try to calculate what is the value of excitation voltage. E angle minus delta will be equal to Vs angle 0. Please remember everything is per phase value, and because it is star connected, we have to divide whatever is the line voltage that has to be divided by root 3. So V angle 0 minus J IS multiplied by XS. And it is unity power factor, so IS angle 0. So we can calculate here E angle minus delta will be equal to 6,600 divided by root 3 minus J times 36 multiplied by 96.225. So when you calculate this as a complex number, this comes out to be 3810.5 minus J3464.1. When you write it in polar form, it happens to be 5149.75 angle minus 42.3 degrees. And please remember whatever we have calculated as delta, that happens to be in electrical angle. So delta is equal to minus 42.3 electrical. If we want to convert this into mechanical, it will be 42.3 degrees divided by 3 because there are 6 poles. This is the mechanical angle. So this is 14.1 degree mechanical. Okay. Now let us try to calculate corresponding to 600 RPM. When we are actually making, this is rated torque. So torque is not changing. And we say it is V by F control. So flux will not change. And it is also at rated when the speed is 600 RPM and it is rated excitation. So we are not even having any change in field current also. So flux will not change. So we already saw in the previous thing that none of the angles will change. Angle will not change. Currents will not change. Only speed will change, and because speed changes, power will also change. So if torque is the same and speed is halved, then power will also be halved. So we are going to have the frequency. Frequency will be 30 hertz because it is half of the original frequency. And excess is going to be, instead of 36 ohms, it will be 18 ohms. Delta remains the same. Delta will remain the same. And what is being asked? What is being asked is what happens to IA, delta, and power factor. None of the angles will change, we already said. Currents will not change. So current will still be 96.225 ampere. And delta will still be 14.1 degree mechanical. Power factor will also not change because none of the angles change. So PF is still unity. So these will not change. Now, second subdivision, let us try to look what is being asked. So the second subdivision that is being asked is if the torque and speed both are halved with excitation remaining the same. Calculate IA, delta, and power factor. So this is what is being asked. So we are supposed to calculate all three. That is IA, delta, and power factor. So first of all, torque is halved. So new torque value is going to be whatever is the rated torque we calculated. Rated torque we calculated was 8753.8. So we should write 8753.8 divided by 2 Newton meter. And that happens to be 4375.5. Now this is equal to 3 EV divided by excess omega S sine delta. So in this particular case, because the speed is halved, we are going to have omega S is going to be 600 RPM or 125.66 divided by 2. And excess is going to be 18 ohms. And E is going to be whatever we calculated as original E, which was 5149.75. It is going to be half of that. So 5149.75 divided by 2. Similarly, V is going to be 3300 divided by root 3. Instead of 6600, I am using 3300. So all these values are known. In this equation, we know what is the torque value. We know what is E, what is V, what is XS, what is omega S. So we should be able to calculate delta. So new delta value, what we have calculated from all these things, is equal to 19.6 degrees. So this is the new delta value. Now, because we know E, we know V, we can say E angle minus 19.6 degrees is equal to Vs minus J times Xs multiplied by Ia angle phi. So, we can write this as E value, we have got already 5149.75 divided by 2, angle minus 19.6 equal to 3300 divided by root 3, angle 0 minus J 18 Ia angle 5. Now we should be able to segregate this equation into real part and imaginary part. So we can write 1905.25 plus 18 Ia sine phi. This is the real part. So we have, this is the right hand side of the equation. So this is RHS of the equation. That is this portion. So that is going to be equal to 5149 divide 0.75 divide by 2. And we have to take only the real part. So that is going to be 2425.68. So this is the real part. So similarly, we have to write imaginary part, which is actually 863.746 is equal to 18 Ia cos phi. We are just writing this Ia phi equal to Ia cos phi plus J Ia sin phi. And we are just segregating the real part and imaginary part. So this is the imaginary part. So using these two portions, we can calculate IA. IA happens to be 56.02 ampere and cos phi happens to be 0.8565. And here the excitation remains the same, but the load torque has been decreased. So this will have a leading power factor. Here we have taken phi to be positive also, which indicates clearly it is leading power factor. Sin phi also comes out to be positive. That's why. So we have solved for the power factor. We have solved for IA. You also solved for delta. All three have been solved for. Now, the third subdivision, what is being asked in this particular numerical example is for above base speed operation. So in the above base speed operation, what is being asked is calculate torque and IF at rated IA and 1500 RPM unity power factor. So we are supposed to calculate what are the values of torque and IA when the machine is operating at rated IA and at 1500 RPM at unity power factor. So first of all, rated speed is 1200 RPM at 60 Hertz. So 1500 RPM speed will be attained at 60 multiplied by 15 divided by 12. So that is 75 Hertz. So the operating frequency here is 75 Hertz. So excess value will be 36 multiplied by 75 divided by 60. So this happens to be 45 ohms. So excess value is 45 ohms. Okay. And Vs is frozen at 6.6 kV line voltage. So Vs will not be changing at all. Okay. So if the machine's voltage is frozen at 6.6 kV and the current is frozen at rated value and it is at UPF, the power will be again 1.1 megawatt. So the power is frozen at 1.1 megawatt and that is equal to root 3 VL IL cos phi. Okay. Now the torque we can calculate at this point. Power divided by 1500 RPM is 157 radians per second. So we can divide the power by 157 radians per second. So that is going to be torque. And power happens to be 1.1 megawatt. It is 1.1 multiplied by 10 power 6 watts. Now the torque value, what we get is equal to 7006 Newton meter, which is very clearly lower than what we had as rated torque. Rated torque we had calculated as how much? It was some 8753.8 Newton meter. So compared to that, currently the torque is lower, clear. Okay. Now, we should be able to calculate what is E angle delta. That should be equal to Vs angle 0 minus J XS times IA angle 0, because this is also unity power factor. And Vs is 6,600 divided by root 3 minus excess is 75 ohms, 45 ohms. This is 45 ohms. And IA is rated value, which is 96.225. So this comes out to be 5768 angle minus 48.65 degrees. So the new value of delta electrical is this, and this is the new value of excitation voltage. But we also know E is proportional to IF and frequency. So I can say originally our excitation voltage was 5149. So 5149 was proportional to 60 hertz and 12 ampere of field current. Now 5768 is proportional to 75 hertz, and what is the IF mu value? This is what we'll have to calculate. So we can use the equation 75 multiplied by IF nu divided by 60 multiplied by 12 equal to 5768 divided by 5149. So from this, we'll be able to get what is IF nu, and IF nu value comes out to be 10.75 ampere. So when we are looking at lower value of torque being supplied by the machine, and we are at a unity power factor, the excitation can be decreased anyway because the flux is also decreased. So this is going to be definitely lower, right? So this kind of explains how the synchronous motor functions in variable frequency, variable voltage mode of operation using a voltage source inverter. Only disadvantage in this particular case is that for every variation in the frequency, the motor will go through hunting oscillations, and after hunting oscillation, it will settle down in the new speed. And if an application does not tolerate hunting oscillations, in that case, this kind of V by F control will not be working well. So in that case, how do we really control the speed of a synchronous motor drive without having any hunting oscillation? This particular case of controlling the speed of the synchronous motor drive without any hunting oscillation is self-controlled mode of operation. So self-controlled mode of operation for the synchronous motor drive essentially is used in many of the applications where the motor's rating is very large, and even a small amount of oscillation or vibration is going to play havoc in the system. So typical applications for self-control cases, one is induced draft and forced draft fans in power stations. So whenever we are having a boiler and we want to have combustion taking place, we have to induce a draft so that there is sufficient amount of air used for, that is present for combustion. And similarly, once the combustion happens, if the flue gases have to be pushed out through the chimney, then, for that you have to again force essentially the flue gases out. That is done by a forced draft fan. So these will be of a few megawatt ratings, and they should not have vibrations and things like that because of their mere large rating. Otherwise, it can actually create a lot of vibrations, which is not good for the structure at all. Another typical example of self-controlled mode of synchronous motor drive operation is in ship propulsion system. So in ship propulsion systems, if we are talking about the ship being propelled by an electric motor, it has to be at least a few megawatt level, and invariably synchronous motor drives are used for this purpose. And here, if we are talking about very large capacity motor being driven, then the converter also has to be of large capacity. And when the converter is of large capacity, naturally thyristor devices will be the natural choice. So these thyristor devices that can be used in a ship propulsion system along with the synchronous motor drive, those generally operate in self-control mode. The third application, typically what is seen is for starting gas turbines in a combined cycle power plant. So in a combined cycle power plant, which operates at a very good efficiency, generally there will be gas turbine which will work as the prime mover. So for cranking up this gas turbine, generally this kind of self-controlled synchronous motor drives are used. So one major difference between the VSI fed synchronous motor drive and self-controlled synchronous motor drive. One of the major differences when we look at them is in VSI fed synchronous motor drive, frequency is available as an independent variable. Whereas in the case of self-controlled synchronous motor drive, we will actually synchronize the inverter which is supplying the synchronous motor drive stator with the rotor's velocity. So rotor velocity and stator supply frequency are synchronized. So the frequency is not available as an independent variable. So F is not an independent variable. So it is depending upon the feedback that we receive from the rotor side. So that is the reason why here at every frequency change, whenever the frequency is changed, hunting oscillations occur before the motor settles down in its new speed. Whereas you will not see any hunting oscillation at all in this particular case, because always there is synchronization between the stator supply frequency and the rotor velocity. So no hunting oscillations. So no necessity for damper winding in this particular case. But only thing is, if we want to adjust the impedance that is manifested by the stator winding, what is depicted by the stator winding to the inverter, that can be manipulated with the help of damper winding resistance, because it will damper winding impedance, it will come in parallel. So the damper winding, if at all it is used, it is only for manipulating the synchronous reactance that is manifested by the stator winding. And in self-controlled synchronous motor drive case, there is no commutating components, external commutating components used with thyristor inverter, SCR inverter. That means it is going to function as a line commutated inverter. So the machine has to work in leading or unity power factor. Whereas if you look at this in voltage source inverter fed synchronous motor drive, the inverter is a voltage source inverter which has self-commutating devices. So this can be built only at limited rating. Whereas with thyristor, you will be able to make the converter work at very, very high power capacity. And because it is unity power factor, most of the times you can say all the current that is drawn by the synchronous motor will be converted into mechanical power. So this will have better efficiency, and you can have inverter rating can be lower. And especially if this is being used in mainline traction, that is long distance trains, then very easily we can incorporate regenerative braking. Regenerative braking can be very, very easily incorporated in this particular case. So we will be able to retrieve a lot of energy. So the basic structure or the circuit of the self-controlled synchronous motor drive. It is somewhat like this. We are going to have three-phase power supply, let us say, coming from the grid. Let's say this is A phase, this is B phase, and this is C phase. We are going to have a normal thyristor converter connected here. I am showing a three-phase thyristor converter. So we are going to have, let us say, this as device number 1, this as device number 3, and this as device number 5. And this is going to be T4, this is going to be T6, and this is going to be T2. And we are going to have this giving out a DC link voltage. So what is available here is, let us say, the DC link voltage. Now A phase is connected to this leg, B phase is connected to this leg, and C phase is connected to the third leg. Now there is going to be a DC link inductance which is converting this DC link voltage into a constant current. And on the other side, we are going to have one more thyristor converter. which is going to work as a line commutated inverter, and this is going to supply the synchronous motor drive. So we are going to look at these three phases directly being connected to the synchronous motor drive on this. And let us say this synchronous motor is probably having a salient pole. So let me show the rotor as well. And maybe here is the salient pole structure in the rotor. So let me connect this to the synchronous motor drive. Now, if we call this as A phase, this as B phase, and this as C phase of the synchronous motor, then this is going to be T11, this can be T33, and this can be T55, and this will be T22, this is going to be T66, and this is going to be T44. Now, normally, this AC is going to be converted into DC. So this is going to be working as rectifier, and this is going to be working as an inverter when power is flowing in this direction. So we call this as the source side converter, and this is the load, because load here is your synchronous motor itself. So this is going to be load side converter. And when we want this machine to undergo regenerative braking, in that case, the roles are going to be reversed. Whatever was working as a rectifier now will work as an inverter. And whatever was working as an inverter will work as a rectifier. And power will flow in this direction during braking. Whereas power will flow in this particular direction when we are talking about motor. So when motoring is happening, the source side converter will have a firing angle which is less than 90 degrees, and the inverter which is connected on the load side, if I may call the firing angle as alpha L, that will be greater than 90 degrees. And because we have the voltages, terminal voltages of the synchronous motor available here, the firing angle will be calculated with respect to these terminal voltages of the synchronous motor. And correspondingly, this firing angle is going to be greater than 90 degrees. And these voltages, what are available at the terminals of the synchronous motor, they are going to help in commutating the thyristors in this particular load side converter. Whereas when we want braking operation to take place, under such a situation, our source side converter firing angle has to become greater than 90 so that this functions as an inverter, and load side converter has to function as a rectifier, so its firing angle will become less than 90 degrees. So it is essential for us to have a good amount of voltage on the terminals of the synchronous motor drive so that these devices are commutated without any difficulty, without having any external commutating components. But when you start the machine, the speed is literally zero and voltage is proportional to frequency. And frequency will be literally zero because the speed is zero. So the voltage, the terminal voltage will also be not available when you start the machine. So the commutation of these thyristors will not take place successfully whenever we are actually starting the synchronous motor drive, self-controlled synchronous motor drive initially. So we need to find an alternative approach somehow to commutate the thyristor in the load side converter. So what we are going to look at first of all is starting operation of a self-controlled synchronous motor drive. How exactly that works? That we have to find out. The second thing is, once it is started, we need to look at the exact analysis and functioning of speed control operation. Once the self-controlled synchronous motor drive is up and running after the starting operation is completed, how exactly the speed control operation takes place, this we need to analyze. So we will be doing this in our next lecture.